Welcome to a short video. In this one I plan to describe just some of the fundamentals of Ampere's Law and to introduce the idea of a line integral in case you haven't seen it before. But I'm not going to get into much application of Ampere's Law because that's done pretty well in your textbook, although I might make another separate video that describes perhaps a solenoid, which is a pretty common example of when we would use Ampere's Law. One way to describe what Ampere's Law is and what it does is to compare it to something that we did with electrostatics, and that is Gauss's Law. I describe Gauss's Law as a nice shortcut for finding electric field expressions for pretty common arrangements such as spheres and point charges, long lines of charge, and then sheets or plates of charge. We were also able to use Gauss's Law to kind of work backwards, and that is if we knew what kind of electric field we have, then we could figure out whether we had charges in a particular location and where they might be. Now in the case of Ampere's Law, we're going to use it to find expressions for the magnetic field produced by maybe arrangements that you're not familiar with yet, but that we'll be using somewhat commonly. The main one is the solenoid. We'll be dealing with those in the laboratory. We will not do anything with a toroid, which is kind of like a solenoid wrapped into a ring, and two different applications for long straight wires. The magnetic field outside a long straight wire and the magnetic field inside a long straight wire. And all of these wires have to be carrying current, so they show actually here the little red I symbols for the current going through those wires. So let's take a look at the actual form of Ampere's Law and describe what each part means. So here's the form of Ampere's Law that we use in our textbook. On the left side, we have an integral sign that has a circle around it. And you might not be familiar with that, but that is known as a line integral. And the circle just refers to the fact that when we do this line integral, we're going to do around an entire closed loop. Now we also can use this back with Gauss's Law. Gauss's Law, we were not doing a line integral, but instead we were doing what's called a surface integral, because we were dealing with the surface areas of things such as spheres or cylinders or boxes. So the circle there is just to remind you that you must go around an entire path from one point back to that same point in the process of doing the integral. And I'll show you what that looks like in a second. And what you're taking the integral of, and remember what an integral is, it's just the sum of a bunch of little contributions to a bigger value. And the values that we're going to sum together is a product, in particular a dot product of a magnetic field value dotted with a small little segment of length. And both of those have directions, and I'll show you what those look like in a moment. So the rest of the Ampere's Law, on the other side, we see mu naught. That's what's known as the permeability constant. That's kind of our fundamental constant when it comes to magnetism. And then we have current. And in our book, we use a subscript through, and I'll explain what the through means. So this is just an important fact of magnetism, that every time you calculate the sum of all these little B dot DS's, and I sometimes refer to this as the magnetic circulation. That's not used in our textbook, but I've seen it used in other sources. Every time you sum all those up around a particular closed loop, you will always get a value equal to the permeability constant times the total amount of current piercing through that particular surface formed by the path. So everything on the left and right side kind of go together here. So here's a diagram that I've got, and we'll use that to kind of illustrate some of these things. I'll blow it up for you. So whenever you do this line integral, you have to do it around a particular loop. And kind of like with Gauss's Law, it's a little arbitrary what shape you use, but in most practical applications, there's kind of certain shapes that make sense. We call that loop the Amperian loop. And so they've got one drawn here just in brown. And it's just kind of randomly drawn in any old shape. And you'll notice that we've drawn it around a few wires. There's actually 3 wires in the region here. 2 of them have current going outward towards you, and one, the one labeled I2, has current going inward, away from you. So that means that there's going to be a magnetic field in this region formed by all of those currents. Now, I have no idea what the magnetic field would be. I wouldn't even try to find out what it would be. Mapping a magnetic field is just as hard as mapping an electric field, which you've been through in the lab before, and not a lot of fun. But let's just say that at every point around this region, there certainly is going to be some value of a magnetic field. We've got one drawn here, just kind of some random point. So that would be like the B values that we're talking about. If we could imagine having that B vector drawn at every single point on the loop. So again, I'd maybe find a point right here and say, okay, what would the B value be right there? Which way would it point? And another spot over here. And I'd have to do that everywhere around the entire loop. So then on the left side, what I would do is I would just take a little walk around my Amperian loop, and I can pick whatever direction I'd like to walk around it. They've got it shown kind of a counterclockwise fashion here. And I would bring my little Blue's Clues notebook with me, and I would write down at every single point what the strength of the magnetic field is. I would multiply that by a small little step right at that location, and then I would dot the two together by accounting for the parallelness between them. And that just means taking the cosine of the angle in between them. So here, on this example, we've got the B vector. We've also got the little ds vector. That's a small little step. It's got to be really small, otherwise you're going to find that your magnetic field value is different. And then you've got an angle in between those two directions. So you do all that, you go around the entire loop and you sum them all together in your Blue's Clues notebook, and that's what you get on the left side. And what Ampere's law shows is that that will always be equal to the fundamental constant mu naught times the total current piercing through that path that you made. So what is piercing through the path? Well, in this particular example, I3 is not piercing through the path, so it does not get included anywhere on the right side. What you would do is figure out how much I1 is contributing and how much I2 is contributing, and you would add those together. So if those happen to be equal amounts of current, they would actually cancel each other out because one is in and one is out. And if one was bigger, then we would have a net current through there. Now the other practical matter is, well, how do we figure out whether to call things positive or negative? Because direction is important. And of course there's a right-hand rule associated with that. Here's how this goes. Once you pick the direction for your Amperian loop, and that was chosen for us here in this figure, but it is completely arbitrary and your choice, so they chose a counterclockwise fashion for this one. Then you curl your right-handed fingers in that fashion, and notice in this case when you curl them counterclockwise that your thumb points out towards you. That means that any current coming out towards you is considered positive. So that would be like I1. And anything going in to the screen away from you would be considered negative current. But if somebody else had chosen the opposite direction for their Amperian loop, well then their currents would be exactly opposite. It does not affect any final outcome. We would still figure out what the net magnetic circulation is. We would just go about it a different way. So there's the meaning behind all the symbols in there, and you can of course clarify a little bit more by carefully reading your textbook, and then take a look at how it's actually employed when you look at solenoids or long straight wires in finding out their magnetic fields.